Welcome to Maths with EJD. In this video, we continue with linear programming where we talk about special cases in graphical solutions. I already made a video talking about a special case in graphical solutions, and which bothered on having multiple optimal solutions. And I actually showed an example of how a linear programming problem can actually have multiple optimal solutions. So in this case, we are talking about infeasible solutions. So infeasible solutions simply means that the solutions don't exist because there are no feasibility regions basically, and we are going to see that pretty soon. So infeasibility in linear programming refers to a situation refers to a situation where no solution exists. No solution exists that satisfies all of the all of the given constraints, all of the given constraints. Okay, this can occur. This can occur when the constraints define regions. When the constraint define regions in the solution space, in the solution space that do not intersect or overlap, meaning there are no points that meet all the criteria simultaneously. Okay. So infeasibility is a critical concept, to understand because it indicates that the proposed model or problem setup may need to be revised because of course it's like a dead end, so to speak, in linear programming. So when an infeasible region is identified, when an infeasible region is identified, it can lead to insights. It can lead to insights about the constraints, okay, and help decision makers understand limitations or misalignments in their objectives. Okay, so that's the idea of infeasibility. Now, to demonstrate this, let's take a problem. Uh, Imagine this problem to maximize z equals x plus y, subject to x plus y greater than or equal to 5, and then x plus y less than or equal to 3. And so, of course, we have the non-negativity constraint that x and y must be greater than or equal to 0. So imagine that this is what you have. So as usual, you know how we do it. so this is line, you're going to get line one from this, and you're going to get line two from this. So you already see that line one would be x plus y equals 5. And if that is the case, then you can say that at x equals 0, of course, when x is 0, you have y to be 5. So from there, you have 0, comma 5. Then on the other hand, at y equals 0 now. So when y is 0, it means x is equal to 5. So in that case, you have 5, comma 0. So that's for line 1. Then when we go to line 2, line 2 is x plus y less than or equal to 3. Okay, so x plus y. Of course, for the line now, we don't care about the inequality. So x plus y is 3. So again, at x equals 0, you can see that y is 3. That means you have 0, comma 3. Then at y equals 0, that means that x is equal to 3. So you have 3, comma 0. So there's no other line to consider apart from the non-negativity constraints. So with this now, we can plot our points. So you have this. So so we have, this is x. So you just have 1, 2, 3. You can even have 4. This is the origin. 1, 2, 3, 4. And this is y, okay? So in that case now, so for the first line, so you have 0, 5, 5, 0, okay? Okay. I need to extend it. I need to extend it. So this should be like 5 now. Then for this also, I need to extend. Okay. 5. So x-axis, y-axis. So there's 0, you need 0, 5. Okay, we can go green for that. 0, 5. This is actually 0, 5, and this is 5, 0. Okay, so we can connect the 2 points with straight lines. So if you use actual graphs, scaled graphs, it's easy to do this. But here we're just doing some kind of rough sketch. So, and now as you're drawing this, it's better you get the region of interest immediately. So this is x plus y greater than or equal to 5. So greater than or equal to is above this line. So it means you're going to shade above this line. Oh, okay, there's not a lot of space above, but it's okay. So, this is above this line now. And this is your line 1. Okay. So for line 2, right? For line 2, we have 0, 3, 3, 0, 0, 3, 3, 0. So that means 0, 3, 3, 0. Okay. And then we have this straight line. Interestingly, this is x plus y less than or equal to 3. So less than or equal to 3 simply means we shade this other part. Okay. And then there is nothing again. There's nothing again. So at the end of the day, you discover that, okay, this is now line 2. So line 1 and line 2, they don't have any points of intersection. So there's no point, there's no point of intersection. If you follow all the ones we've been doing, you have, so normally we should be looking for where green lines intersect black lines. But in this case, none of the two lines intersect. So there's no solution, in short. And that is basically the idea of infeasible solutions. So the solutions are not feasible. You also want to demonstrate it using Desmos. Desmos is that very nice uh, graphing calculator you can use like that. So Desmos, okay. So we have, of course, you want to do x plus y is greater than or equal to 5. So you can see that line there, that red one. Then you have x plus y is less than or equal to 3. So you see, they do not intersect. So at the end of the day, there's no feasible solution for that problem. Basically, that's what that is about. So that is basically infeasibility of solutions. That's what it means. So, and we see this properly demonstrated here. All right. So, if you have not subscribed to this channel at this point, be sure to do that right away and hit the notification bell so you can always get alerted each time a new video is released. And comment, let me know if you want me to teach a particular topic, whether in Python or in mathematics, any math topic for that matter. Then, Of course, you also want to like and also share with other people so that they can get to know about all of these great things that we're teaching around here. Till I come your way again, keep optimizing. Bye.